partial fractions. The integral, this, is equal to, okay? So look at the integral we can deal with. So we're given something that, okay, so first thought is we look at substitution, because substitution is usually pretty much the easiest one to do. But that's not really going to be an option here. So you look at u equals x squared plus 3x plus 2, du equals 2x plus 3, and you try and figure some way where we can change this to fit into that, and it's really just not going to work. So the easiest way to look at this would be probably partial fractions, especially since it looks like we can break this up into two polynomials. So if we rewrite this, purple, purple, my favorite flavor. So we have, let's see here. So I'll start with writing 5x plus 8 over x squared plus 3x plus 2. And I'm going to assume that equals a, nope, not yet. So I'll do 5x plus 8 on top, break up this polynomial into x plus 2, x plus 1, and you can do that either by inspection. Inspection is kind of the fancy word for a guess and check. You're just like, all right, I feel this can be a polynomial, so two numbers that when multiplied together give you 2, but when you add the numbers together, 1 plus 2, you get 3. The other way to go through that, which is more cumbersome and less pleasant, is the quadratic formula. Negative b plus or minus b squared minus 4ac square rooted all over 2a. Either one will work. The inspection, guess and check, will be faster. So after we have the polynomial split up, we're going to assume that this can then further be broken up into a over x plus 2 plus b over x plus 1, where they did combine the denominators. They created a common denominator and then combined the fractions. So what we do is we write it like this. There's a couple more rules for partial fractions. We won't go into those here, but they're worth knowing. Like if you have a x plus 2 quantity squared, or if you have a quadratic in the denominator. So then what we do is we rewrite everything back as the first fraction. So we recombine the denominators. So we do x plus 1 over x plus 1, x plus 2 over x plus 2, and then we recombine it into x plus 2 times x plus 1. Now I know this kind of feels like we just went in a circle. We kind of sort of did, but that's okay. The idea here now is when we multiply this out, we're going to get 5x plus 8 from right here equals a times x plus 1 plus b times x plus 2. And this is just algebra. I say just algebra as if it's easy and can just forget about it. No, there's a lot of difficulties with algebra in life. Alright, so then this is what we're left with. We see that, oh, we can cancel the bottoms because they're the same. Simplifying the left and right side, we get 5x plus 8 equals ax plus a plus bx plus 2b. Rewrite that in terms of x a plus b plus quantity a plus 2b. And then from here, it becomes semi-obvious, kind of intuitive, that, all right, you have your x's here, you have your x's there, you have your not x's there, or x's to the 0 if you'd like. And so we have 5x equals x times a plus b, and we have 8 equals a plus 2b. I know I've changed colors so many times on this. Ridiculous. 5 equals a plus b. A equals 8 minus 2b. Okay. So then a equals 5 minus b. 5 minus b equals 8 minus 2b. Add 2b to both sides. We can have b equals 3. So we move the 5 over here, 2b over there. A equals 5 minus 3, which equals 2. Okay, so we have a equals 2, b equals 3. And your first thought is like, wow, that was quite the adventure. Yeah, partial fractions can be, which is one of the reasons why, when possible, I try to avoid partial fractions. Not because it's hard, but because it's kind of tedious. And every time you make a new calculation, it's just one more chance to make a mistake. So if you can avoid it, you're probably better off doing that. Okay, a equals 2, b equals 3. Going back up here, so we have integral 0 to 1 of 2 over x plus 2 plus 3 over x plus 1 dx. So we said you have this is equal to the blue part right there. Yep. And now this equation gets much simpler. So to do this, I'll just focus on this one to start with so we get the idea. So we'll pull out the 2, 0 to 1, 1 over x plus 2 dx. We'll say that u equals x plus 2, du equals dx. And so we're left with 2, 1 over u du, which equals 2 natural log of u, which we then convert back to natural log of, I think there's x plus 2. And then this will be evaluated from 0 to 1. And so what you see is we do substitution, but it's a pretty bland substitution. And it's the kind of thing you can kind of do in your head. So you can be like, oh, this will be 2 natural log of x plus 2. So I'm going to rewrite this real quick. So this will be right here. 2 natural log of x plus 2 plus 3 natural log of x plus 1 plus 1. And we could probably combine those, do like a little power thing, and not worth it. So, and this will be evaluated from 0 to 1. And so I have 2 natural log of 3 plus 3 natural log of 2 minus 2 natural log of 2 minus, running out of room, 3 natural log of, I think 1. 0 plus 1, 1. Yep. Change colors for the umpteenth time. This will go to 0, which is convenient. This will go to 1 natural log of 2. So we have 2 natural log of 3 plus natural log of 2, which gives us natural log of 3 squared plus natural log of 2, which can then be combined as natural log of 3 squared is 9, so it'll be 9 times 2 which will be natural log of 18. Take that answer, zoom out, move up, compare. Aha! We even got an answer that's the same, which is good. Whoop. So after that excessive amount of work, 90% of which was algebra, we finally get the answer, natural log of 18. So to backtrack, we see this integral that we're going to integrate. We try to do substitution. We look for something that's going to be a derivative of something else, and we hone in on this x squared and this x. We try it. We see it doesn't really work, until we go on to something else. In this case, we look at the bottom and we're like, okay, we can separate out the bottom. It's a polynomial. We can not foil, but defoil. Separate into two separate polynomials, x plus 2 and x plus 1. And something that's just done by intuition, something that's done by guess and check. If nothing else, it's done through the quadratic formula. After we do that, we then do the partial fractions method. We find out that a equals 2, b equals 3. We're then left with two relatively easy integrals using natural log, which we can do through substitution to make it a little bit easier, but not really necessary. Once you see the kind of the pattern, the format, you can get that one. And we solve a problem, and we get natural log of 18. And that's how you do a relatively simple partial fractions problem. Now, in hindsight, it's like, wow, I took a long time to do that. That's true. You would really only be given a couple minutes to do this problem. I took like 10. So when you're doing this, you have to move quick. I dilly-dallied quite a bit, and you're going to be prone to error. The goal here is not to be perfect. It's just to be pretty good and correct more often than not. So do your best, but you do have to move quickly. That's how you do this kind of partial fractions problem.